vai começar e vai dar uma contagem. Certifica disso.
Já pode chegar já? Já que nós podemos começar aqui, não? Eu acho que tem que ser certo.
Talvez. Não. Mas depois ele dá uma definição melhor.
Ok. De noite someone else is coming? Rodrigo. Rodrigo, I saw Rodrigo. Who else? Da tua, Rodrigo. 1, 2, 3, 4, 5, 6, 7. Faltam os dois Rodrigos. Que horas são?
1h34.
1h34? Então. Só falta um Rodrigo agora.
Para a gravação ficar melhor, existem 3 posições que a câmera fica. Então, se eu apertar um lá, ela vai dar um pouco no lugar, tá vendo?
Mas tá bom assim.
Mas ela melhora, entendeu? Tá vendo? 2. 3.
Mas aí não mostra tudo.
Não mostra. Mas o Ricardo estava falando que seria ideal fazer esse zoom. E aí, alguém da sala pode se voluntariar a fazer esse trabalho de apertar 1 e 2 para aproximar.
Mas vai ser difícil, porque a pessoa vai esquecer e vai perder partes do quadro.
Então, eu posso deixar no padrão sem problemas. Acho que...
O que vocês acham? No padrão normal, alguém já viu alguma aula depois? Alguém já tentou ir ver alguma aula para ver?
Eu tenho que ter a primeira, dá para ver, tipo, o quadro fica um pouquinho pixelado, né?
Sim.
Fazer. Dá para assistir.
Dá?
É só subótimo.
Sim. Vocês preferem fazer no botão ou deixamos assim? Assim dá para ver tudo, mas não é preciso fazer nada. A outra maneira faz zoom nos dois lados, fica melhor, mas tem que alguém estar a carregar em 1 e 2.
Se alguém quiser.
Olha lá, esse é o zoom 1.
Eu vou esquecer.
É direita.
Não vale a pena,
Não vale a pena, né?
Ficar,
tá bom.
vamos lá.
Deixamos no padrão.
Fica a responsabilidade. Imagina depois me xinga, né?
Não, eles me xingaram por causa do áudio no primeiro vídeo. Tranquilo, você vai deixar parado, porque tava muito na frente, assim, fica estourado. Ele vai colocar mais embaixo.
Tá bom.
É isso, obrigado.
Obrigado.
Boa aula.
Obrigado. Bom, okay, so let's get started. So we have an easy paper today. I think, at least compared to the previous two, this one is a bit easier. It's also, on the other hand, impressive that he was a PhD student when he wrote the paper. So that puts the bar where you should aim. But so you can write simple papers, that's okay. You should just try to aim at explaining the de Sitter entropy or something like that. Okay, so let's see. So the paper starts first with the observation that the black hole has an area, and that this area of the black hole always grows. And by this statement he makes two comments. He points out that this happens when we throw stuff inside the black hole. Then the black hole, when it receives stuff, grows. Or when you have even more something more interesting, when you have merging of two black holes. And he refers to some nice theorems by Hawking where when you merge, you get some black hole whose area is bigger than the sum of the two areas. And so he says that all evidence we have is that in GR, the area of the black hole is a monotonic quantity. It always increases. So that's, he repeats this statement many times. Right? So, okay, we got it. The area increases. That's fine. And so, of course, the entropy also increases. And so he says, okay, maybe they are the same. Maybe the entropy is just some constant times the area. He points out that by units, if I want to make all units right, there should be some h bar, and so perhaps the entropy is some constant times the area of the black hole, and this would be the entropy of the black hole. So he points out that other functions of the area would not work, but just the area would be a good candidate for being an entropy that represents the entropy of this piece of matter that is the black hole. Then he emphasizes that the entropy of the universe would be the entropy of the black hole plus the entropy of stuff outside. Right? We could have a black hole and some stuff outside. And he emphasizes that what must really happen is that this entropy must always grow. And therefore, we could try to test this idea by having some stuff outside that falls inside the black hole, and so the entropy outside disappears. And the entropy of the black hole increases, and by matching both, we could check if this is true, and not only check, but try to estimate this constant. Okay? So the idea is consider a thought experiment where we have some stuff outside. This entropy of the stuff outside, we are going to describe it in a second, will be simply log 2. We say that it goes to 0 because it falls inside the black hole. And therefore, delta S of the black hole must be at least equal to this log 2. And in doing this, we try to fix this constant. Okay. Okay, very good. So let's go into a little bit of detail of this. Let's work this out in a little bit of detail. So first, he points out that that the area, the variation of the area of a black hole when something falls inside the black hole is always bigger or equal than B. B is the size of the object. So this is some appendix based on some paper of some Greek guy. B times the mass of the particle that falls times 2. So this is the mass of the particle that falls inside the black hole. This B is the size of the particle that falls inside the black hole. So this is just, you take a geodesic that describes this small sphere, you let it fall, and you do some approximation to say that when this sphere touches the horizon for the first time, which means the center of the sphere is some proper separation b away from the horizon, you say at that point it fell inside, some rough estimate, and that tells you that the area is bigger or equal than this. You see that if b was 0, this would be 0. Then you would say, but because you say you always need some size for a realistic object, the area increases at least by this when you throw something in. But then we realize that the size of an object as a function of its mass, mu, on the one hand, we could draw a curve here, which would be b equal h bar over mu, which would be the constant wavelength of the particle. So a particle of mass m has a characteristic quantum mechanical size mu, h bar over mu. And it has a Schwarzschild. If it was a black hole, it would have Schwarzschild radius twice the mass. And therefore, we see there is a minimum value that this guy can attain. And we can even, if we want b times mu, it's even smarter to plot b times mu as a function of mu. And then this parabola will become a constant, and then this will become like this. And so we see that this b times mu, this is always bigger or equal than 2 times h bar. On the other hand, he points out that this entropy of this stuff needs to be at least log 2. So for that he recalls that the entropy is basically the sum of pi log pi, where pi is the probability of finding the state in configuration I. So let's just recall, for example, if I have a bunch of states I from 1 to omega, and all of them are equally likely, where the probability is 1 over omega, this gives me omega times 1 over omega is 1, and you get log of 1 over omega with a minus sign. The entropy is just log of the number of states. This is what we know very well. And so he says that if I have just one particle, the entropy is at least log 2, because I have the particle flying outside the black hole, and maybe I don't know if the particle is really there. And so there is at least that ignorance that maybe it's there, maybe it's not there. And so P is 1/2, is the biggest entropy it could have. And so the biggest entropy you could have would be at least log 2 for the question yes, no, for the particle being outside or not the black hole. And so you see that according to this formula, the variation of the entropy would be some constant times variation of the area over h bar. This should be equated at least to h bar times 2. Actually, sorry, this is the area divided by 4 pi for me. 1 over 4 pi. So this would be, here for me A is really the area, so it would be 8 pi. And if you equate this 8 pi with log 2, and you would conclude that this constant here is log 2 divided by 2 pi with a 1/4 here. And this would be, if you want, his proposal. And he says that this is of course very unwavering, because we have this criteria for when to absorb the particles and so on. And so he says this constant could be half a little bit, maybe by a factor of 2 or something, but it should be more or less this. Now, a posteriori, we know what the correct result is. It's 1/4, so we know it's off by this factor. It's not exactly 2, it's more like 1/4 or 1/5, so it was a little bit more off than he thought. So we know the correct result for the entropy doesn't have this factor here. So this is wrong. We now know. But it's a order 1 number, so the argument is still very good. It's a good estimate of this result. There was finally one more very important thing that's also crucial that I did not mention, is that when you compute the variation of the mass of the black hole, you also know that you get a variation of the area times the number plus other stuff that are not there for Schwarzschild, but something like variation of the charge times something plus variation of the angular momentum times something else. And you want to draw an analog between this and usual thermodynamics, where we have dE equal TdS plus minus PdV plus etc. There are more potentials. And so this part here would be the analog of the various potentials you could have. And then this part we would identify with this part. The energy is the mass of the black hole. And then you would make this identification. But of course, when you make this identification, you see that you can always multiply by h bar, multiply by a constant, provided you divide by the constant. And so this argument of thermodynamics never tells you what's the entropy and what's the temperature. It only tells you that this is the temperature up to a constant, this is the entropy up to a constant, but you don't know this constant. Right? And so once identified, you will identify this with T, this with S, but it will tell you only up to a constant. And then it tries to estimate the constant like this. That's it. We are done. I said it was easy. Yeah. So maybe for completeness, let's compute this constant properly. Okay? But this is what I want to say about this paper. Any questions, comments? Skeptical remarks? Otherwise, yeah.
So, question, because he somewhere in the paper says that a reducible mass, the sum of reducible masses of collection of black holes could be decreased when they merge. Is this true? I don't know.
Oh, of course, because it emits lots of radiation. Oh, that's what happens.
But the radiation could be from the kinetic energy?
Oh, of course. They start with two black holes far away. They are not interacting. They have mass m1 +m2.
Yes.
Now they start approaching and it's spiraling. And while they are spiraling, they are losing lots of energy, lots of radiation, right? So then they finish collapsing, and now you have a single object. That object has much less mass than the mass of the initial mass, because lots of energy was lost in the radiation.
But he said specifically the irreducible mass, which is the mass that cannot be extracted by any process.
But that is when they are very separated, that's just the mass. Right? If you are very separate, that's just the mass. They cannot be, there's nothing like an indestructible black hole or anything. You throw another black hole at it, they will merge.
For black hole, yeah, the mass will be the same. But for instance, if you have two black holes very far away apart, if you're not holding the black hole, they have an initial velocity, for instance.
No, they don't. They start slowly, then they start attracting and approaching. No, they don't need to start with any initial velocity, no? I just separate them a lot. I let them go, right? Like I have two particles that attract each other with two opposite charges. I let them go, they start with zero velocity and they start accelerating.
you're considering your hand putting the particles.
So if you put very far away, of course decays, and they are free. They just have a 1/r potential, right? They feel just a 1/r potential, very, very weak. That slowly starts accelerating, the other one slowly starts approaching, then they accelerate a lot, and when they are inspiring, now they are very strong. Any other questions, comments, skeptical remark?
So, I think it's kind of naive, but from what he writes in the paper, it seems that the first equation that you wrote, S equals S, black hole equals S stuff, is some kind of big point.
Yeah, it's his proposal. It's what's called the Beckstein generalized entropy. Yeah, it's a generalized second law. Yeah.
But at least for me, it seems very straightforward to accept this.
Yeah, I agree.
It doesn't seem so much in the paper.
It's the first time. I mean, now you live inside some culture where this is already part of everyday life. And indeed, I presented it as something. Okay, so let's compute this constant properly, just for completeness, since we are done.
Before we start, can I ask something?
Of course.
This thermodynamic, well, this T and S that we're defining for this system doesn't belong to the thermodynamical variables that we have often on statistical physics, right? Or it is the same?
No, it is the same. Yeah, so he makes the point that he says at some point, be careful, this tip has nothing to do with the temperature. That's wrong, it is a temperature.
But how do we know that?
It's here, right? T
Yes,
it's your temperature. It was just that it was too wild for him to imagine a black hole with that temperature. So he said, well, this is probably not a real temperature, it's just an analogy. So he was afraid to commit.
Yes, because this kind of formula is kind of straightforward. It doesn't match with the knowledge that we have for thermodynamical variables. So that's why I'm asking.
No, it
It's
matches.
more related to
matches.
theoretic information. That's why I'm asking.
Right. No, but it matches. This is thermodynamics, right?
Yes.
And this should be a temperature, so this should be a temperature, and it is a temperature. And later people understood that this is a temperature in two ways. One is the way I'm going to describe, and the other, maybe even more physical way, is Hawking radiation. If I have a black hole, it emits a spectrum of radiation that when I compute the spectrum, it's the spectrum of a body that is at some temperature T that we will compute. And so it really has some temperature, and that temperature is this temperature. Okay, so this temperature, the way to measure it is Hawking radiation. But that was a paper a few years after, maybe 5 or 7 years after this one. So at that time, it was too wild to conjecture the black hole with that temperature.
And it makes up relates mass with energy very easily. Is it direct related?
Yeah, energy is equal to mass. That's just Einstein, right? And you can go to infinity, see how the metric decays at infinity. The way it decays at infinity tells you the mass of whatever is inside, which corresponds to the mass. I mean, yeah, okay. Yes. Okay, good. So let's compute this constant. So let me just. So does everyone know how to compute this constant, or is it worth going through just to explain? Yeah? It is? Okay, let's do it. Okay. So let's do it for Schwarzschild. So let's write the metric for the black hole. As you know, Okay? Everyone agree? So just the usual metric of the black hole. And so first, notice, let's compute first the area of the black hole. So the area means that we set T equal constant, R equal to the horizon radius. It's also constant, so the first two terms are irrelevant. And we see that the area is just the area of the sphere, which is 4 pi times 2m squared. And so we see that m, the mass, is square root of the area divided by 16 square root of, divided by square root of pi and 4. So we are after factors of whole factors, so I cannot do any mistake. So I'm counting on you to help me out. Otherwise, things will not go right. And so, if we compute dm, we conclude that dm is dA 8 square root of pi square root of A. Do you agree? Okay, good. So that's one important formula, which is exactly what we wrote there, that dm will be dA times something. That something we want to identify as the temperature, but we don't know what number we put in dA, what number we leave outside. So now let's compute the entropy by putting the black hole in going to Euclidean. So T equals I tau. So this means that we want to go from E to the I H T. We want to go from E to the minus beta H, right? So we do T equal to I tau to rotate this, right? And what we want to do after we rotate, we want to compute the partition function by doing some trace over e to the minus beta h. So it means, which is computed in the usual path integral, I remind you, by identifying this Euclidean time tau, with tau being equivalent to tau plus beta, in other words, tau plus 1 over the temperature. Okay? Or if you are careful with h bar, it will be some h bar. So, the Euclidean time identification is the temperature of the object. Correct? This is familiar? When I have path integrals, I go to Euclidean time. The periodicity in Euclidean time is the inverse temperature of my object. So let's do it. Let's rotate. We rotate t to I tau. So I will change tau here, and I get a plus. Let's see. And now you see that now everything is Euclidean. And so you see that r equal to 2m, this Euclidean component disappears. So this is the end of space. Now we don't have space-time, we have space. Everything is Euclidean. So this component vanishing is the end of space. And tau is a periodic coordinate. Right? So the way to think is that this will be the radius. Here is when the radius is 2m. And then tau is some periodic coordinate here. And at this point the space ends, and we have what's called the tip of the cigar. Notice that when r is very big, what happens when r is very big? This becomes just a very big r. The metric becomes just dr squared plus d tau squared, which is just a cylinder. So we start with a cylinder that comes and shrinks and disappears. That's the metric we have. But now we have a problem that here, generically, we'll have a conical singularity. And that's not good. So let's zoom in close to the tip and see why we have a conical singularity and how we will fix it. So if we are close to the tip, let's zoom in there. So let's write that the radius would be something like this. So x is small. And then let's work it out. So that factor there would give me, so then the metric close to the tip of the cigar, it will behave as x squared d tau squared plus 1 minus 2m over r is just x squared. dr is 2m times 2 dx times x squared. So you see the x cancels, and this becomes just 4m squared. No, it becomes just 16m squared dx squared. Right? So you see, close to the tip of the cigar, we have dx squared and x squared d tau squared. So this looks like angular coordinates, like r d theta, dr squared plus r d theta, except that we have this 16m squared here. So we have to be careful. So let's factor out the 16m squared. If we factor out the 16m squared, we say that this is 16m squared dx squared plus x squared d of tau over 4m everything squared. Do you agree? And this, we know, it has no conical singularity if this quantity here is identified with itself plus 2 pi. Right? If this was an angle, this is r squared plus r squared d theta squared, then it's just there's no conical singularity. Do you agree? Then I'm really zooming in close to the tip of the cigar, and there is no conical singularity, instead it's smooth. And I zoom in here and I see some smooth plane. Right? So for this to be smooth, I need this identification to be 2 pi. And that tells me that tau needs to be identified with tau plus 8 pi m. And therefore this 8 pi m should be identified with h bar divided by the temperature. And so we learn what the temperature of the black hole is. Sorry?
Can you repeat the identification argument? How do you...
So I'm saying that a system at finite temperature is a system where in the Euclidean path integral, time is identified with time plus beta.
Yes.
So when you find an identification of Euclidean time, that parameter is the temperature, is the inverse temperature. And we just found it because we know it was periodic, but we found that from this point of view of infinity, everything is good. You could put a cylinder, it doesn't matter. But to have a smooth geometry inside, when you go inside, you see that you have a conical singularity. Unless the angle here that you identified is this, and therefore this is the inverse temperature.
Okay.
This fixes the, it's not up to you to choose the, you try to put the black hole in a periodic time, and the black hole told you this is the time, which means this is my temperature. And so we learned that the temperature of the black hole is h bar divided by 8 pi m, which is, once we use that first equation, h bar divided by square root of a and m is square root of a divided by 4 pi, so the 4 gives a 2 and the pi becomes square root of pi. Do you agree? This is t. And so now if I go to that formula here, right, I see that I should write this 8 as 2 times 4, and the 4 I should put here. And now all this we just identified as the temperature, so this is the answer. Okay, and so we conclude that the entropy is the area over 4. Okay?
Does this change if you consider steaming or charged black holes? Or is it the same?
No, it will give the same. It will give the same. See, it's all about zooming in close to the horizon, finding coordinates that make this end of space regular, and if you follow this derivation, the conclusion would always be the same. That the temperature, the expression for the temperature is not going to be this, it's going to be more complicated. But it's whatever it is, such that the entropy is still the area over 4. But what's universal is that it's, because this first equation will also change. The m is not going to be just the a over this, it's going to be more complicated if you have more parameters. And that will also change, but then the final relation that this is the entropy is untouched. And so for all black holes, the entropy is, we conclude that the entropy with all the right factors is the area divided by 4h bar. This is with g equals c equals 1, but keeping h bar. So that's the universal result. And this result here is for Schwarzschild. Then a big question is, once I know that the number of states of my black hole should be the area of the black hole, can I find a microscopic model, like in statistical mechanics, where I really count and derive this result microscopically? Right? So that's what sometimes in some very special string theory setups you can do, but only very special ones. And in general, for this type of Schwarzschild black holes, we don't know how to do it. It's too complicated. But one of the successes of string theory was that for some supersymmetric 10-dimensional black holes and so on, it was possible to really count on the microstate and reproduce this result by an honest counting of what kind of strings and brains configurations could produce this black hole. Which was a very, very independent computation and a nice surprise that it works perfectly. That's the connection between thermodynamics and statistical mechanics. Okay, we started 5 minutes late, we ended 15 minutes earlier, discussing one more paper. So this was really a little bit easier this time, which is good. So now let's randomize who is going to present stuff that is related to this. Yes?
You said that you can also derive this from Hawking radiation.
Yeah, you can also derive Hawking radiation and ask when I have a black hole, what is the radiation that is coming out at infinity? And by looking at the spectrum of the radiation, you know how a body of a given temperature, what it radiates, right? And so you compare the two, and you measure that, you find exactly that the temperature is this.
But it doesn't give you any.
It confirms this in a slightly more physical way, where you say temperature is really the spectrum of a black body, and I fit the dots to some black body spectrum, and I measure the temperature. Really, how you would measure the temperature of a piece of coal if you were just measuring the radiation here. So it's a very physical derivation.
Is there an a priori argument why these two procedures should always coincide?
A priori argument, I mean, because both are correct. Yeah. This was a good argument, the other is also a good argument. They better agree, or physics is inconsistent. It's just the rules of logic. So the next paper is also easy, but it's big. So don't leave it to the last minute. So it's a long paper. So I think it's also relatively easy to read, if I remember correctly. I haven't read it in many years. But it's a bit long. So start now.
We've calculated the entropy, but we could also calculate the pressure using the same ideas.
Yeah, we could compute these other potentials that I mentioned. Yes, for people did.
Alright, so also discovery is that it's not all entropy, but
Yeah, there's a big field of black hole thermodynamics where all these quantities are computed and
okay.
yeah. In sum, a black hole is not different from a piece of coal or from a piece of material. It has temperature, it has pressure, it has everything. So it's more or less the same. And what's remarkable is that it's, if you want, the object with the biggest entropy. If things fall inside a black hole, they cannot get out, so it always increases the entropy, and the black hole is the stuff that will have more entropy than anything else. So if the entropy was outside or something, it falls inside the black hole, the full system grows, and so the black hole is the best thing to have the most entropy possible. So in that sense, they are special objects. Otherwise, they are the same as any other object in thermodynamics. Yeah, like I told you also, for Witten's paper, it's good if you study Tuch's paper from 79 if you did not, about just large n expansion and the fact that planar graphs dominate, etc. Friday is at 10, right? We agreed on 10 or it was 10:30? 10. Okay. So let's see, I have here the names of the people from last time. So give me the names of the people that did not present last time. Alan with one L. One L. Leandro. Dennis with two N's, right? And Egan. Okay. So here it is. Can you see? I will put even bigger zoom, and I will take out from this Rodrigo Aguiar. So Rodrigo will present, but so let's remove Rodrigo. Let's randomly select the other three. Okay? Can you see?
Yeah.
Okay, so Gabrielle, Alan, and Dennis. Raise your hand. Did you guys? Okay, so it's a slightly different configuration. So, and now, so this is the order of the three of you. And now let's do just a random integer to see where Rodrigo Aguiar will fit. Random integer between, say, first position up to fourth position. So random integer 4. 4. So you are the last one to present. You are the last one to present the next week. So we will do Gabriel, Alan, Dennis, No. Because now 5 people, right? So one of the 5 people will not present. We are 9.
One of them will become next week's Rodrigo.
Yeah, one of them will become the week after Rodrigo. Who is not presenting? Raise your hands. Who is not presenting next week?
But there's 2 weeks.
1, 2, 3. You are not presenting, right? No. So raise your hand if you are not presenting. So you see, you are 5.
But there's 2 weeks I don't present. Yeah. So Rodrigo also, he didn't present for 2 weeks.
Yeah, Rodrigo also didn't present.
Finished the first cycle.
It's not enough people. One
It's 9, right? 9 is not divisible by 2. 9, right?
We finished the first cycle, 9 people, and then
There is one.
yeah.
There is an 80% chance that you will get.
Ah, é verdade. Eu pensei que tem que fazer uma coisa parecida com acho que isso é bem legal, né? A gente escolheu um trabalho de pessoal. Que é legal que a gente tem que ser uma ideia assim, e ela tem que ser sempre inclusive fazer perguntas, vai ser tipo, mas pode ser legal, vamos procurar, vamos dar uma olhada depois. Mas se não achar mas vamos pensar até hoje, né? Tem que ser tipo hoje, a gente tem que decidir. Começar a ler, porque a gente ainda tem que resolver tudo.
Yeah, so just one thing. So if you guys want to write binary ideas for what to present, to take it as an idea or not, feel free to write me or a classroom or whatever. Ah, então ideas today. No, this is very basic stuff. You should just check what your linear quantum theory will be. Because of this time is here, right? How do you patent integral? How do you patent integral? You discretize time. But then you take a trace. And this trace, take a tree of it. It's just that you are not doing an evolution from in to out state. You are computing a partition time. You are taking a trace. Right? Trace means the sum over all space, and where the first and last are the same. Because I value is the sum over I. And so it's really discretized, and that's why the time is generally. And moreover, it's identified that we are really taking a trace in the periodic activity. You evolve and it must be published. So you sum over fields that are like
perhaps I'm not entirely convinced by here. Perhaps I'm just missing some key stuff. But the point is, when you go when you analytically continue, you go to Euclidean space, you find this singularity, and then the horizon singularity is coordinate singularity generally. So you're just switching coordinates to see if you find some. Yeah. So you're trying to wait.
In Euclidean, it's a real space building instead. It's not like there is anything beyond the article plan.
Okay.
This is Euclidean, space disappears there. That's fine. Volumes are zero. Other ones will go. So the topology is just CR topology. So we went from 1 hour to 3 hours.
Yes.
Covering only an epsilon.
Is there any easy way to see why the log 2 vanishes?
Why the log 2?
Because in his the estimate he gives, there's a 1/4 of log 2 over 2 pi. And the log 2 comes from that thing in
You want to
information
say,
theory.
could there be a better argument that gives
Yeah.
this a closer approximation? Right?
Yeah.
So you saw that he predicted an entropy that's a bit too small, right? So his entropy was too small. So it means that the area should grow, when you throw stuff inside, the area should grow more or less. It should grow. Right? It's about this one model. How much does the entropy increase when the particle falls in? And he had this estimate of the area depending on the size of the object. But maybe it is not when the sphere just touches. Maybe there are some quantum effects that when it's slightly far away, it's already by uncertainty principle, maybe it starts settling inside and then into average. So you could try to improve that model to make it more and more realistic. You will never get the correct result. It's very hand waving, and but you could try to argue. I don't know if people did it. That's the question. If people now we know how to derive things in a cleaner way, like I explained. But are there recent papers that said, oh, now that we know that this argument was not perfect, how do I improve it to make it better? I don't know. I should check the literature. That would be something nice to explain. You guys are not.
But it's where I'll look.
But you could still look.
Yeah.
Suggest to the other ones that are presenting. I think that'd be nice. I don't know. Did someone ever revisit this argument after people knew the correct result? Or they just said it's a hand-wavy argument, it's correct, up to order one, we don't care anymore because we have a better one.
So the idea is that we underestimated the entropy conclusion.
Right. So let's see. We had some log 2, and then we divided by stuff, and we don't want to divide by so much stuff, right? Because we divide and got a number much smaller than 1. So we wanted to divide by log 2, so that it was just 1/4. So we wanted the factor that was there, we wanted to be smaller, so we divide by something smaller. So the increase in area should not be as big as he said. This 2b, this area being 2b times mu is too big. Perhaps maybe it's not like a sphere just touching, it's not enough. It needs to be halfway inside. Maybe it's if we got more precise and I don't use just one particle with a yes or no, but I use something many like particle. Yeah, you could ask if there's a better experiment that measures them to be more precise.
Maybe the log 2 is too big. Instead of the.
No, you want the log to be this.
No, too small.
Yeah, too small. Yeah,
Yeah, the log 2 is the minimum you can. It's yes or no.
Right.
Yeah.
Yeah,
It's the last structure.
But these are all good. There is one argument, secondly, I want to go back to the example, but these plots are the minimum size, like this and like this, they are hand wavy, it's schematic, it's correct, always up toward the mark. Was it still useful? Or in this case, the paper was enough?
No, it was.
No, it was
You mean this last part?
Everything.
Oh, yeah.
I was not sure.
No,
Maybe this lecture feels